The best way to find the gains for your PID controller are to derive the equations of motion of your system and then use systematic methods from linear control theory to find good choices of the gains. Now, often we can still design a good PID controller even without a good model of the system. And the way we do that is doing empirical gain tuning. So we're going to try an example of that right now. So first you might want to choose some reasonable gains for your system based on how much control effort you know is available and how much error you can expect to have. So we're going to start with some reasonable gains, but first let's take a look at our system over here. This yellow line represents what we're trying to control. Maybe it's the position of a robot arm. This white line represents our reference signal. So initially the reference is 0 and then it jumps up to some value and stays constant. That's called a step input to our controller, and therefore what we're going to be looking at is the step response of our controller. So this is a simulation written in MATLAB. Let's try some gains for this unknown system. So PID tests, and I'll start out with a negative value for my proportional gain, 0 for the integral, 0 for the derivative. And if I have wires to the motor hooked up backwards, for example, maybe I need positive gains, maybe I need negative gains. So this will just be a test to see whether I need positive or negative gains. So I press enter. And you can see here that the response of the motor went the wrong way. It's not going up, it's going away from the desired value. So that means I need positive gains. So let me try again with a value of 1 for the proportional gain and 0 for the integral and derivative. And now we can see that the output rises closer to the reference value, but it's still not doing very well. So this is my first guess. I'm going to mark that with a 1. So this is my K sub P axis for proportional gains, K sub D for derivative gains. And my first guess here was at K sub P equal to 1, K sub D equal to 0. Since I'm still far away from my desired value, I need to increase my proportional gain. So let me raise it to 10. And now you can see that we're coming closer to the desired value. So this is my guess number 2. But we're still pretty far away. Let's try increasing it by another factor of 10. OK, now we're getting closer, but we still have a lot of ringing and overshoot here. So let me mark this as guess 3. For the heck of it, let's try increasing the gain by another factor of 10. OK, and now we're not getting any improvement in behavior. And in fact, if we took a look at our control signal, we would see that because we have such large gains for K sub P, that the control signal is always saturating. It's always at its maximum or minimum limit. So we're getting this kind of strange looking behavior here. And that says we've probably gone too far just in the K sub P direction. So let's backtrack a little bit and try adding some damping. So we'll reduce our proportional gain to 100, make the derivative gain 1. And I see that. There's not much of an effect, so this is guess number 5. Let's try increasing that by a factor of 10. So we're going to increase the derivative gain by a factor of 10. You can see it damps out a little bit, but still not very much. We're getting a lot of oscillation and overshoot. Let's increase by another factor of 10. OK, now we're starting to see more damping. It's still oscillating a little bit. So that's up here. Let's try increasing the damping by another factor of 10. OK, now we're getting something that looks pretty good. So we're getting this smooth rise and settling. So this is guess number 8. Okay. So this response doesn't look bad. We still have some steady state error. Let's try increasing the stiffness and increasing the damping together, hopefully thereby keeping the good shape of our response, and this is called the transient response, while hopefully reducing this steady state error. So I'm going to double both the proportional and the derivative gain. So K sub P is 200, K sub D is 2000. Okay, now I'm getting even better performance. Still the good transient response, less steady state error. So this is guess number 9. We've increased in both K sub P and K sub D. So let's stop there with our PD gain tuning. And by the way, we can't make our gains arbitrarily high or else we're going to see chattering behavior. Now let's try adding a little bit of integral action. So let's start out with Ki is equal to 1. So keep P and D as they are. And if you notice here now, the response starts slowly heading towards the desired steady state value. So we're seeing some effect of that K sub I. Let's increase by a factor of 10. Okay, now we're seeing that we're getting essentially 0 steady state error, but we've introduced a little bit of overshoot. And that's what integral gain will do. While it tries to reduce steady state error, it may induce some instability. And if we wanted to emphasize that, we could increase that gain to 100. And now you're seeing lots of overshoot and oscillation. So we've gone too far with K sub I. So if we go back here, it looked like 1 was pretty good, looked like 10 was pretty good, but maybe somewhere in between. Let's try 5. And now this is a nice looking response. We get the 0 steady state error fairly quickly, and there's no overshoot. So things you care about in your response are how much steady state error do you have here, and do you overshoot, and how long does it take to settle? So here it settles to, say, within 2% of the final value by around here or so. So the faster that happens, the better. The less overshoot, the better. And the less steady state error, the better. If you're working with a second order system, like a force controlling a mass, it's almost always best to start by tuning the proportional gain and then go to the derivative gain, and to save the integral for last. Again, it can have a destabilizing effect, so you have to be careful with its use.